Hello, everybody. So we have been learning a lot about differentiation. We have been able to differentiate many types of functions. One thing we have not addressed yet is differentiating compositions of two or more functions. And this requires a new rule, a very effective and powerful tool called the chain rule. And that's what we are about to learn in section 3.6. So let's get into section 3.6, the chain rule. All right, so the question is, we know how to differentiate the sine function. And the answer, surprisingly, maybe you got used to this already, maybe it's not surprising anymore, but for some miraculous reasons, the derivative of the sine function happens to be the cosine function, right? One thing we have not been able to do so far is to do something like this. What's the derivative of the sine of x square function? And you could just sort of think, well, it has to be the cosine of x square because that just sounds reasonable, right? It turns out that's not quite the correct answer. What happens when you have composition of two functions? And that is the theme for today, the chain rule, section 3.6. All right, now consider what happens. This is a completely new type of question. we haven't seen any composition that we have differentiated yet. So consider y is equal to f of g. Oh, by the way, I hope you have realized that this is a composition of two functions. First, you do x squared, and then you do the sine function. And for convenience, we will call the first thing you do the inside function. It's not a technical term. It's the term I have been using for years in explaining the chain rule. And then the sine function is what you do second or last, right? And typically, this is what I have been calling this the outside function. All right, inside function is called the inside function because often you see this inside the parentheses. And also, this is something that you do first, and you see that inside of a larger context. All right, so here, g is the inside function, f is the outside function. Now, you know how to evaluate this, right? You do g first, despite the fact that f is appearing first as you read from left to right. As I mentioned a few times before, this is a two-step process. X gets thrown into the box called g, and out comes the outcome, g of x, and that is immediately thrown to another box called f, and the result is f composed with g of x. And I have explained that if you get this bigger box and put these two boxes in there, that is the composition f dot g. Again, you do g first, right? So that is what happens. Now, what would you do if you have to find the derivative? Now, remember the derivative, the concept of the derivative has to do with the rate of change, all right? And so because you have two things composed, you do g first, and x is thrown into this, and g has its own rate of change, right? So you have the derivative of g involved in this. And so x may go, let's say, increase by 1 unit. G of x may increase by, say, 3 units, okay? The derivative of g at this particular x may be 3. So as x moves 1 unit, g moves 3 units, okay? And then f has its own derivative. Let's say the derivative of f at this input, g of x is 4, okay? So then as g increases by 1 unit, this increases by 4. But remember, x is thrown in first, and g may cause the derivative of g may be 3 at x. Let me illustrate what I'm talking about. This is confusing, right? So I have pre-drawn this picture, and it looks like the series of chains, and really where this is where the name of the rule comes from. Even though, by the way, most books don't even have the chain picture or any chain picture. And many students sort of miss the idea of where this chain rule has come from, right? What I was saying is, let's say you have this x, okay, and that gets thrown into g of x, and I'm going to call this g of x u, right? U, for some reason, the lowercase u is often used in calculus as a sort of a substitution variable, all right? So g of x, we're going to call this u, right? Now, when you put u in here, this is the function g, and this is the function f. F is going to take f of the new input, which is now called u, okay? But this is really f of g of x, which is what we expect as the composition. All right, so what I was saying is, let's say this g has the derivative 3 at x. And so that means for each increase of 1 in the, for each increase in x by 1 unit, g increases by 3. And that's what the derivative means. Instantaneous velocity, or the rate of change, is 1 to 3. All right. F, on the other hand, takes any variable u, and let's say the increase here, or the rate of change, is 4. So as u changes by 1 unit, increases by 1 unit, f of u increases by 4 units, right? So this is like, 4 miles an hour or so. All right, so that's what's happening. All right, you see that? So what happens is, as you rotate this wheel or gear, sort of like the gears you see in the bicycle, and you have, if you have like a 14-speed bike, you have 2 times 7, right? And so, all right. So if you rotate this one complete cycle, this goes around once, but the middle one goes around 3 times, and that's what we mean by 1 to 3, right? So as x turns around as you turn x one rotation around, the middle one goes around 3 times. Now, I said the ratio between the second and the third gears is 1 to the 4. So as you turn this once, this goes around 3 times. And that means this goes around how many times? Okay. For each turn here, this gets rotated by 4, right? So if you turn this 3 times around, this will go around 12 times. So what is happening here? Okay, let me let me try to illustrate what I'm saying. One turn here, I think you got this already, right? Causes 3 turns here, right? Now, 1 turn of this will cause 4 turns here. So for 3 turns, it's going to turn 3 times 4, which is 12 turns. All right, and mathematically speaking, this is what I'm saying. Du, see, g has the derivative of 3 with respect to x. So du dx is equal to 3. And what I'm saying here is that dy, see, y is f of x, right? So this is y here. Okay. dy du, so if you take the derivative of y, f of g, with respect to u, which is, g of x, this is actually 4. And what I'm saying is dy dx is actually the product of these. That's 12. I think if you look at the series of chains and gears, you can see where this number is coming from. It's pretty obvious that you have to multiply these 2 numbers, 2 derivatives together, right? So you have 2 derivatives involved in here. One is g with the derivative of g with respect to x, and the other is f, the derivative of f, with respect to u, which is sort of like this intermediate result, which is g of x. I know it's a bit confusing because we have never really analyzed the composition of 2 functions this way. We have to figure out the rate of change for each, right? But because you have a 2-step function, it makes sense by looking at this gear and chain picture that you should multiply the 2 derivatives together. All right, now I have used what is called, so let me go ahead and write this down. All right, this part illustrates the chain rule written in sort of a weird way, right? dy dx. So what we said is let u be g of x. right? And so y is f of g of x, which is f of u, right? So what I have concluded by the picture in this chain is that dy dx is the product of this, which is dy du, times the product of this and this, which is du dx, and this is the derivative of the first part, and this is the derivative of the second part, and you multiply together. This is called the chain rule. Unfortunately, this is really hard to apply, right? So I'll show you another much easier to understand way to describe this. But the chain rule, written in what we call Leibniz notation, is this. Okay. Now, this is actually a pretty important way to state the chain rule, because in later, like in Calculus 3, you'll see more different chain rules because you study different, the higher dimension functions and so on. So it is nice to remember this, even though this is not very practical to implement it. All right, so keep that in mind. But another thing to notice here is that these derivatives sort of look or behave like fractions, right? So you see du's cancel each other, causing you to have dy dx. So that's another way to take a look at or to analyze these. Think of these as fractions. Okay, but again, the important thing is you multiply two derivatives together, right? So here is, as I promised, a little better way to explain this, right? So let me restate the chain rule in a way that is a little easier to understand. If y is f of g of x, then the derivative of y with respect to x, okay, is, you see that? This is the derivative of f with respect to u. So that would be f prime, but with respect to u, which is g of x. And you multiply that by the derivative of u with respect to x, which is g prime of x. And you say, well, is this supposed to be easier to understand? Yes, it really is, okay? And so here's what we are, maybe a bit more details so you can more easily understand this, all right? So what I'm saying is the derivative of the composition is going to be the product of two things. The first one is the derivative of the outside function evaluated at the inside function. See, g of x is the inside function, right? Followed by, multiplied by the derivative of the inside function. Okay, it looks confusing, but it's not as bad as it appears or it sounds, okay? And I am very confident that all of you will be able to do this very quickly and learn this very quickly. And in fact, it's good that you will do so because you're going to use this like every single day for the rest of your calculus career, right? This is so useful. And that the reason is because many functions we have are not really, product or a quotient. Certainly we have many functions that are sums or differences of 2 or 3 or more functions, but you will see a lot of compositions, okay, in real applications. So anytime you have a composition of 2 or more functions, you will have to use this chain rule. All right, so let me give you some examples, because the way to understand or to master many concepts in mathematics is by looking at examples, right? All right, so let's say we had this function, sine of x squared, right? And I said that the derivative is not cosine of x squared. So what is that? Here's the way to think about this. Remember, this is sine of x squared. That means f of x is what? Sine of x. Okay, I should have written the g of x first. All right, g of x, let's note, g of x is x squared. That's the first thing you do. And then f of x is sine of x, right? So the composition of these two functions is f of g, which is sine of gx, sine of x squared. All right, so the derivative is going to be, now follow this very carefully. Follow this very carefully. Maybe I should get a little brighter color. All right, so the first thing you do is to take the derivative of the outside function. So that's a sine, and that becomes a cosine, right? And the argument is simply going to be exactly the inside function, that's x squared. All right, so the sine squared becomes cosine of x squared. Now, isn't that what I said you should not do? Right, well, this is the first thing you do. And then you multiply this by the derivative of the inside function. So now you look inside of the parentheses, that's x squared. Let's take the derivative of it. All right, so this is the solution. Now, typically we write 2x first. So the answer, the derivative of sine of x squared is 2x times cosine of x squared. Right, so that is the correct answer using the differentiation method by the chain rule. All right, now I have been talking about the inside and outside functions. Think of this as a blob, or like just an object, which is like the quantity, right? So sine of blob, okay, that's what we have. Sine of blob. What's the derivative of the sine of blob? The answer, cosine of the blob times the derivative of that inside blob. Right? So, and you can just sort of think of this as a big fuzzy cloud or something. You know, the sine of the cloud, the derivative is the cosine of the cloud times, and then you look into the cloud and take the derivative of it. When you think this way, I think it's a lot easier to understand and apply these functions. Again, here, x squared is called the inside function. The sine square is called the outside function. All right. By the way, let's check with something that we already know, okay, to make sure that the chain rule is actually working. I mean, it's working because it's a theorem and somebody proved it years ago, centuries ago. And you know, once it's proved mathematically, it can't go wrong. Let's say x is 1 over x, the reciprocal function, right? Which can be written as x to the negative 1, right? And g of x is x cubed. Okay, now do you know what f of g of x is? That would be f of g of x, that's x cubed. But what does f do to the input? Whatever you put into f, it's going to take the reciprocal. So that is the composition of f and g. You can write this as x to the negative third, right? So that's our y. All right, let's take the derivative of y. That is, well, that's the power rule applied here. So you have -3 times x to the -4, or you can rewrite this way if you'd like, right? So that's not a problem. We can clearly understand that, right? All right, so but we can also write y as, here's the way to write this, because you have f, the reciprocal after the g, you can think of this as x cubed, that's the inside function, and then take the outside function, which is the inverse function, right? Right, can you see how you can apply the chain rule here, the inside outside? Not, I mean, this, we use the power rule first, right? The power rule gives you this answer, but if you think of this as the composition of two functions with the inside and outside, what you can do is you take the derivative of the outside function. Now, this is the blob I was talking about. The blob is what's inside, okay? Think of that as a cloud. So the derivative is going to be -1 to the -2nd power of that blob times the derivative of the inside blob, okay? Now, what is the blob? That's x cubed. And if you simplify this, this is simply what? Negative x to the negative sixth power times 3 to the negative square, right? So this will be 3 squared minus 3 squared over 6 x to the sixth power. And that's negative 3 times x to the negative fourth power, which is, of course, exactly the same, right? So that is chain rule, the chain rule at work. And you can see that this actually gives you the right answer. And you should not hide the fact that you feel really, really good when you get the answer that you are supposed to. All right, so that's the first part of the the chain rule. Now let's summarize this, since it's so new, and it's something that you will have to carry with you for the rest of your mathematical career, probably, right? The chain rule would be a part of your life, whether you like it or not. You might as well, learn to live with it, because the chain rule is not going to leave you alone. It's going to haunt you if you don't attend to that. All right, so to differentiate a composition of two functions, and by the way, if you have more than two functions, to compose y with, then you apply the chain rule repeatedly. And again, it sounds terrible, but it's really not that bad. All right, number one, differentiate f and evaluate, let's say, and evaluate it at g of x. That's what I mean by this. So you take this, and it's basically -1 times whatever is inside to the negative second power. And so that something, or whatever it is inside, is called the blob, and that's g of x. Right? By the way, blob is what I am using in my lecture. I would not certainly write that in the textbook if I were to write a book, because that would be published, and it's sort of embarrassing to call something a blob. All right, so differentiate f and evaluate it at the blob, right? And that would be f prime of g of x. And then find the derivative of the inside part. And then third, multiply them together. So you end up with f prime evaluated at g of x times g prime of x. It is striking, maybe. It may be weird to know that what I just said is equivalent to this Leibniz notation, but it really is the same thing. This part is the f prime of g of x, and this is g prime of x. All right. I hope this is clearly understood. All right. Now, in the second part of this video, for the same section, 3.6, I'm going to give you many examples, sort of practice questions. And then we'll go into maybe using an example where 3 or more functions are put together. And then we will go on to the next section. All right, so let's go to the second part at this point.